Okay, we're in chapter 1 still on ingredients of change, functions, and limits. And this is section 1.11, which is cubic functions and models. So the characteristic behavior of cubic functions, well, they're written as the form f of x equals ax cubed plus bx squared plus cx plus d. So with that cubic part, that makes us have a lot more terms here. And here we can't have a equals 0 or it wouldn't be a cubic, it would become quadratic. And then so all of them, a, b, c, and d are constants, and our input value is our x here, okay? Now the constant a is called the leading coefficient, and d is going to be when f of 0. That's at f of 0, and that's going to be our y-intercept. So wherever it hits that y-intercept, that's going to be our d. Now, cubic functions have one of the four shapes. So, and I've noticed they're all unbounded. So as you go to negative infinity or to positive infinity, they just keep going up or down all the way. So depending on which one you have. So this is the one where it increases from left to right, then it comes down and decreases for a while, but then finally increases again. So it increases at the end and at the beginning. Now this one decreases at the beginning, then increases, and then decreases at the end. So whatever it starts doing is what it ends doing. Now this one's increasing the whole way, and this one is decreasing the whole way. So those are the kind of the four graphs we'll see with cubic modeling. Now, I've kind of mentioned a little bit about the end behavior here. So when we have a greater than 0, that's when we're going to have it increasing. And it's going to increase at the end as well as the beginning. And it can be a continuous increasing, or it can be an increasing followed by a decreasing, then back to increasing again. Okay, but in either case, it's concave down at the beginning and then concave up at the end. And you can see that in both these models. We have an inflection point somewhere in there. Now, when we look at our limits, as we go, x goes to positive infinity, our y goes to positive infinity too. And so our limit of our function, whatever the function is going to go to positive infinity. And when we go to negative infinity, our y is going to go to negative infinity. And so our limit will be negative infinity. And that doesn't matter, as long as a is positive, whether we have a change in direction or not, that's going to be the case. Now, when a is less than 0, so if we have a negative 2.5 or something, then we're going to be decreasing at the beginning and decreasing at the end. And sometimes we don't change direction, it's just decreasing the whole way. Now, when we change directions, then we have a different shape here. Now, the limits are going to be basically the opposite of what we just had with a greater than 0, because as we go to negative infinity, that means we're going to go up to positive infinity. So as x goes to negative infinity, our output goes to infinity. And as x goes to positive infinity, we're going to go down to negative infinity. And so that's what we get here. Okay. And so that's kind of our end behaviors. Now, scatter plots are going to be sometimes harder to look at. And so, here we have 4 different scatter plots, and it shows the data sets that could be modeled by a cubic equation. So oftentimes what happens is a portion of the cubic function appears to fit extremely well for a data set. And so, but it can be actually modeled with a quadratic function. So in an effort to keep things as simple as possible, this is how we're going to kind of look at it. So if the scatter plot the set of data fails to exhibit an inflection point, it's not going to be appropriate to fit a cubic equation to the data. Now, as with all models we use, caution is necessary when using the cubic models to extrapolate data, beyond our actual data points, because then we're not sure, does it really go down like this, or does it, all of a sudden it's just kind of keep going up, or something else, maybe it's a 4th degree or 5th degree and it's going to do something different, but we've modeled it as the cubic, and so only in that region is it going to actually fit the cubic model, and out beyond that, it's anybody's guess as to what it actually does. So here we added a few more steps in choosing a model. Now notice one thing once we get to it, we've actually added the next section in our book 1.12, the sign, but we've added it in here anyway. And so looking at the curvature of the plot of data, if it appears to lie in a straight line, okay, well, we're automatically going to say, okay, it's a linear model. But if it's curved but has no inflection point, we can either be, quadratic, exponential, or we can have a log function. And then if it appears to have that inflection point, then we're going to try the cubic, logistic, or eventually we'll look and see the sign. Now we're going to look at the fit of the possible equations. So when we look at the step one here, it should result in narrowing the possibility to probably two choices. So, if we're looking at the quadratic exponential log, we might not have something that actually has a tailing off going to 0. It might actually come down and it's just going to keep going down. So we know it's going to be either a log then or a quadratic. But if we see that it tails off like this and it goes to the end behavior close to that 0, then it's going to either be exponential or quadratic, because maybe over here but a little further it actually goes up. So it's going to give us usually just two choices to choose and compute. And so what we're going to do is we're going to compute those equations and then graph them on a scatter plot of the data. And then the one that comes closest to the most points, now it doesn't necessarily have to go through the most points, just has to come close to the most points, is usually the normally the better model to choose, okay? Now, then we're going to look at the end behavior of the scatter plot. If step 2 does not reveal one, a model is obviously better than another. Consider our end behavior of the data, and then choose the appropriate model at that point. And make sure you consider the context of the model, because sometimes, it's going to do something and the context says, oh, hey, it's going to continue going up no matter what. Or someone might say, well, it's going to flatten out. And so things like that are really going to determine, oh, well, hey, even though it fits really better with the model that goes up, it contextually it should go to that one. So we'll use that model instead. Now, sometimes two models are equally good and they both would fit perfectly for the set of data. So in that case, again, like I said before, we just choose whichever one and go with that, and that's going to be our model. All right, so we'll stop there and then we'll start exercises.